Next, we're going to discuss permutations. And permutations are just a more sophisticated way of counting and just one special attribute. And so permutations talks about the beginning of how order would matter. Now, we're going to start off because we're going to be using a symbol that's called a factorial. So we're just going to start off discussing the factorial first, and then we're going to be able to jump right into permutations. So let's just look at a simple example. Let's say I have a 4-letter word, math, and it's to be arranged to form a 4-letter code without using one letter more than once. How many different ways can I arrange them? Okay, well, if I have 4 letters, M, A, T, and H, and I rearrange them to make a 4-letter code, then I have a first character of a code, the second character of the code, the third character of the code, and the fourth letter of the code. And if I have 4 letters, right, M-A-T-H, which is 4 letters, then how many do I have to select for that first letter, right? I can choose any one of these. I can choose any one of these 4, right? So I would have 4 to pick from. But if I'm only picking one letter and not using it again, how many do I have left from the 4 if I already picked one? I have 3, right? And then 2, and then 1. So if I use the multiplication rule, I would get 4 times 3 times 2, which is 24. So there are 24 ways of arranging the letters, can make a 4-letter code without reusing the letters. So when I have a total number of choices and I multiply them down to 1 and not using decimals, just fully whole numbers, and just have like something like this, like 4, 3, 2, 1, and multiplying them, this is a special product. And we call this product the factorial of that number. And in this case, because my first number was 4, this is called 4 factorial. And if I say 4 factorial, that means that implies to any reader that it's going to be 4 times 3 times 2 times 1. If I did a million factorial, that would be a million times 999,000, 998,000, and so on, all the way down until you reached 1. And so the factorial, which is an exclamation point to most people, but to mathematicians, it's called a factorial. And essentially, that's all what a factorial means. If I give a whole number with a factorial after it, that just means I'm multiplying that number and every whole number there before it down to 1. So this can get a little strenuous because if we have 4 factorial, that's doable, right? But again, what if I have like 25 factorial or 100 factorial, right? We need a more sophisticated way of entering this in like technology or writing it out. So now let's take a look at a simple example. If I said how many ways can 5 different door prizes be distributed among 5 people? So once again, I have 5 people. Okay, and if I have 5 different door prizes, that first person has 5 choices. But the second person only has 4 choices for the prize, and the third 2, 1. So what factorial is this? Well, we see that 5 is the very first one, so we call this 5 factorial. If I put this in the calculator, I could go over here and put in maybe 5 times 4 times 3 times 2 times 1. But that's not sophisticated enough, right? Because what if I had 120 factorial? Am I going to punch in my calculator 120, 119, 108. No, there is a factorial in your calculator. So let's go ahead and take a look. So if I wanted to put 5 factorial in the calculator, I would just hit 5 and the factorial symbol. Your factorial symbol is hidden inside your math menu, which is right under alpha. So hit math and go ahead and move the cursor all the way over to probability. So make sure the prob or probability menu is highlighted and you'll see 1 through 8. Notice number 4 is what you would think an exclamation point, but it's actually a factorial symbol. So go ahead and hit 4. And now you have 5 factorial. Your calculator knows what this is. It's 120. So if we wanted to do the previous example of 4 factorial, we could, and we get 24. So you can see the calculator is getting more and more sophisticated as we move along in the class. And it's about to even get more sophisticated. Okay, so this was equal to 120 ways to give out the door prizes. Okay, now let's look at a cool type of example. So we have 8 sprinters and they want to make it to the Olympic finals. And Olympics only has the gold, silver, and bronze medals. So how many different ways can we award them? Well, if I have 8 sprinters and only 3 medals, that means only 3 people are getting the medals, which are the categories, right? Gold, silver, bronze. And then how many, and the choices, right? How many choices do I have for each? Well, if a person gets a gold medal, they're not going to get the silver too, right? Every person just gets 1 medal. How many people in the beginning of the race do we have to win the gold? Well, if we have 8 runners, right, that means we have 8 people for that gold. But that person now has the gold. How many people left to get the silver? Right, 7. And how many left to get the bronze? 6. So using the multiplication rule, we can easily multiply this, right? And if we did this, it would be 336. So that's how we would do it if it was asking the question, how many different ways, right? There's 336 ways we can give out 3 medals out of 8 people. Now, that's not really why I have this problem, because it's not factorial, is it? I cannot say that this is 8 factorial. Because 8 factorial means I would have 8 times 7 times 6, and then times 5 times 4 times 3 times 2 times 1, right? I don't. Notice I only have the first 3 of the factors of the factorial, right? Okay, well, let me kind of play with this a little bit, funner. Let me write this and say, closer look. Let's say I do have 8 factorial. And I said, okay, that's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And notice that I only had these 3 up here. How would I get that with 8 factorial? What would I have to do in order to reduce out all these factors here? Like all these factors have to, 5, 4, 3, 2, 1, all have to go away, so then I could get 8 times 7 times 6 up here, right? Well, the only thing we're going to do with factors, meaning multiplication, is do the opposite, which is divide. So technically, I could divide by 5 times 4 times 3 times 2 times 1. And then all those factors would reduce out, and I would be left with the 8 times 7 times 6 that I need for my choices. And these would all reduce to 1, right? Because 5 divided by 5 is 1, 4 divided by 4, right? We all know that's 1. That reduces out. So if I went ahead and divided by 8 factorial by what? What is 5 times 4 times 3 times 2 times 1? Let's look up here. What is 5 times 4 times 3 times 2 times 1? 5 factorial. So if I said 8 factorial divided 5 factorial, that is the same thing as completing this problem above. Would you agree? Okay, so now, even a closer look. We have now, again, 8 runners and 3 medals. How in the world would I get 5 from the numbers 8 and 3? How would 5, this is not coincidental. It's not coincidental that I would reduce out by 5 factorial. What is the relationship between 8 and 3 to get 5? That's right, you would subtract. So furthermore, I would write this as 8 factorial over 8 minus 3 factorial, where now this 5 is rewritten as 8 minus 3 factorial. And again, that if I did that in the calculator, that would still be 336. Either way, this is what we call permutation formula. We have just proven and developed a permutation formula. If we say that we have these many categories and these many choices where the choices aren't the number of categories, then we can easily just take the number of choices and divide by the number of choices minus the number of categories factorial. So it's a really cool formula, and this is what we call a permutation, where our number of categories doesn't match the number of choices we have, unlike up here where we always have the number of categories to match the number of choices. So permutation says, well, no, what if you don't always have that? Then just divide by that difference factorial and you'll go ahead and get the same answer. So in general, we have permutations where order matters, right? And then without replacement, because we don't replace the metals, right? So just like the door prizes above, right? If this person picks a door prize, they don't get to pick again and again and again, right? The one door prize is gone, it's done. Once this person gets the gold medal, they don't get another medal, right? So permutation is exactly this, and it's going to be where order matters: gold, silver, bronze, president, vice president, secretary, right? And we do not replace anybody. Everybody, once they're taken out, they're taken out. Let's look at the formula now. So here, if our items are selected from n choices, we have n pick r, npr is equal to the number of choices factorial over the number of choices minus the number of categories factorial. So up here in the previous example, right, we would say that n is equal to 8, r is equal to 3, and we would have 8 pick 3, which is 336. And if we did this in our calculator, permutations are in that math probability menu. In fact, you would see NPR. Notice number 3 has a C there, and that's combination, and we're going to do that next. So let's go ahead and select number 2. And notice it gives me the prompts for N and R. So here I would put 8, move the cursor over, pick 3, and that would be 336, which is exactly what we got. Okay, so now let's go to an example. In how many ways can people in a 1,000 person marathon finish first, second, and last? So the first thing we want to know is that order matters, right? Someone who is third or last is not going to be happy with being first, or that should be first, right? So order matters, and without replacement. Because once someone is first, they don't get to be last, right? Okay, the next thing we want to notice is that we have 1,000 people to pick from for 3 places, right? And so we could do this one of 2 ways. The first way is noting that n pick r is going to be 1,000 pick 3. The next way is saying, well, if I'm going to do the multiplication rule. I have first, second, and last, and my choices are 1,000 people here, 999 here, and 998 here. But either way, we will get the same answer. So let's do both in the calculator. So here I'm going to have math, probability, and number 2, and put 1,000 in for choices, and I'm going to pick 3. Next, let me go ahead and put the product of 1,000 times 999 times 998. And notice that they're the same no matter what. So you can use the hangman spaces if you like, or permutation formula. Either way, it seems like it'll be the same amount of work as long as the number of categories is low. If you get to 20 categories, you're going to want to use the calculator formula for sure. So let me write down the answer, which is 997,002,00. So 997,002,000. So if you think about a marathon and 1,000 people in a marathon, for 3 places, there's 990,002,000 possibilities for 3 places. That's so crazy, huh? It's a lot. Okay, now let's go ahead and try passwords. We love passwords. They're made of permutations. How many 5-character passwords can be used using the letters A through Z if repetition of letters are allowed? And what about if repetition of letters is not allowed? What is the difference between these 2 scenarios? Okay, so there's 2 scenarios happening here. So let's go ahead and split them up. So the first one is when repeating is allowed. Okay, well, 5-character passwords, that means 1, 2, 3, 4, 5, right? And the number of choices for each character are the letters A through Z. And so therefore there's 26 letters in the alphabet, but I can reuse the letters. So even if I use one of the 26 letters on that first character, how many choices do I have for the second character, knowing I can repeat letters? Well, yeah, just the same, right? 26. In fact, it's 26 across the board. So here I would use the multiplication rule, but have 26 to 1, 2, 3, 4, 5 power. So notice that here, that's the number of characters, and then this is the number of choices. Okay, now let's go to non-repeating. So you can non-repeat the letters. Okay. So now we could say, well, if we cannot repeat the letters, that means we have 1, 2, 3, 4, 5 characters and 26 choices on the first, but I can't reuse that letter, so I need to have 25, 24, 23, and 22. And using the multiplication rule, we can just multiply. Another way to look at it again is to say, well, I have 26 choices and I'm going to pick only 5 of them to make the password. So this is a permutation because once again, it's without replacement, okay, and order will matter. Remember with passwords, if my password is math, MATH, can I put that in any order I want? No, right? I can't put THAM, THAM, right? And say that's my password. It's the same characters. Why doesn't it work? You can't do that. Passwords are permutations. That M should be first, A should be second. It's very important that order matters. So when order matters and you have without replacement, meaning non-repeated characters, it becomes a permutation. Okay? And when repeating is allowed, like over here in the first case, then everything's out the door, right? It has nothing to do anything now with permutations. It's just counting at that point. Okay, and so the difference is one is a permutation and then one isn't. Okay, and then if we wanted to, we could go ahead and put this in the calculator. I don't think it's that important, but we can do it for practice. So go to math and go to probability and go to number 2, and then let's go ahead and put 26 pick 5. And so we'll have 7,893,600. Okay, if we wanted to see what 26 to the 5th was, I mean, that is ginormous, right? Yeah. That's going to be 11,881,376. So when order matters, you're going to have less options, right? Whereas when repeating is allowed, it's going to even be bigger because you're allowed to reuse the choices.